Okay, let's get started. So I'm Jun Nakajima from Intel. I presented the NFV last year, and so I'll talk about the updates since last year. And the people here are basically, contribute to this project and then this presentation. Okay, just a credit to them. So we have a KVM enhancement project for NFV at the OPNFV. So I'll talk about basically what we are doing there, basically. Then especially the deterministic execution and the minimal latency. And then the other one is the inter-VM communication. Basically, we propose this one. The name is kind of tentative. So, but it's kind of reflect how we do that, okay? Just to recap, refresh your memory, just in case you forgot what the NFV is. But essentially, this is, the software. In short, software is replacing the hardware, right? So you have, today, we have a hardware network appliance. And the idea of NFV or vision is to consolidate those hardware network equipment types onto the the volume standard servers using IT virtualization technology. Okay, so typical kind of framework. This is a very kind of conceptual picture, but it's not just a hypervisor. You need to have orchestration like OpenStack and also SDN control like Open Daylight. And then you can find that NFV infrastructure powered by KVM container. And on top of that, you have VNFs. Those are the ones that the hardware equipment today, and that we those will be replaced by software. So that the latency and then high performance are critical because basically software is competing with hardware, right? Otherwise, we cannot achieve that kind of thing. Okay. With that, then to accelerate that kind of NFV adoption, last year, I think last October, OPNFV consortium was established. Then the KVM is crucial to the OPNFV because the OPNFV depends on those upstream projects, Linux and the KVM, OpenStack, and then Open Daylight. And as you see, many companies are there. I think I kind of believe you guys are there, right? So, okay. Now, in fact, last month, we proposed a project which is a KVM enhancement for NFV that was approved. Now this is official project at the OPNFV. Okay, so we are focusing on basically 3 projects. One is minimal interrupt latency and inter-VM communication. Then the third one is fast live migration. I don't talk about fast live migration today because the next session in a different room will cover this one. Okay, and for the first one, thanks to the Rick and Lian yesterday, they covered that real-time KVM, and this one, the first one, heavily depends on that real-time KVM. So I can actually save my time. Skipping the details and just review at the high level, okay, and also show some number that we have, okay. So again, this having a deterministic execution or the minimal latency is critical for NFV. Okay, so just recap where those latencies are coming from. There are synchronous events like interrupt or VM exit or cache misses or TL misses. They can happen at any time asynchronous fashion. So somehow we need to minimize those asynchronous events. Or if they happen, we will need to mitigate that handling of TLB misses. Okay. Now, software also can have an issue. For example, if you have a spin locks and you don't know how long it takes to get out of the spin lock, or if you have mutex, right? And Rick yesterday also talked about the need for the real-time kernel, Linux, right? So the software is also important, and also your applications, right? If your applications are not real-time ready, then you cannot expect any real-time behavior, of course. And other thing is exit to the user level, which means, for example, in case of a KVM, if you exit to the QEMU, I think also people talked about. I think Jan or somebody talked about. Also Rick talked about the issue with QEMU, right? The other thing is the hardware. So Rick also talked about SMI. Oh, this is nasty, right? we really need to work with. We really want to work with hardware vendors, make sure they can disable SMI for NFV purposes. And power management, like a CPU, deep state. If a processor enters the deep state, and then it takes probably sub-microsecond or something. Depending how deep the state are, it takes some time to get out of the deep C state. And sometimes the NIC itself can cause some latency if you have if you don't use a QoS feature of the NIC, especially combined with SRB. So those are kind of the cause of latency. I just want to talk about the kind of high-level solution, and this is a summary of what I think Rick or Jan mentioned. So we need some exclusive allocation of resources, especially, for example, CPU or memory, right? So typically, we need to have partitioning, okay? This can be done by also ISO CPU or C groups, okay? And we want to use huge pages to mitigate the TLB miss, because if you have large pages, then deferring a TLB is much faster, okay? So we really want to use a huge page table of huge pages. And software. So we need a real-time KVM there, okay? Not just a host. We also need a real-time guest. Otherwise, even the KVM is supposed real-time. Its guest doesn't provide real-time capability, then you don't get real-time. The other thing is the hardware technology. We have, for example, the cache allocation technology or the advanced BT features. Okay. Probably I don't need to cover this one as Rick mentioned this one, but I have probably a picture, so then you can see the picture. It's essentially you can partition the last level cache for applications or VMs so that we can increase the determinism, right? And what it's really telling is you have two options, okay? One is limited cache or unlimited cache with noisy neighbors. So which do you choose? Okay, and our test and performance measurement shows it's better to go with the limited cache for you. Otherwise, this, the noisy neighbors gonna take your cache away and consume. Okay. So there are many presentations going on. We have IDF right this week. So if you're interested in, look at the white papers, presentations. Okay. So I have the data. Okay. This is similar to what Rick showed. Of course, because we are kind of working together. So the machines are different, but we have a kind of very similar result. And if you look at more than 97% are there, right? You can see, right? And there's there are 5 outliers, right, which causes maximum latency, which is 5 out of 80 million. Okay. This is a total number, okay, basically 80 million. So this outlier, the occurrence of this one is less than 1 occurrence per 10 million. Okay, so this is a good number. But this is a cyclic test and kind of, not really it's not using a device, PCI device, or when a system needs to work with PCI NIC devices. This may not reflect what you see. Now I have other data which uses real hardware. Okay, in this case, what we measure is that the latency in the interrupt handler in the guest. Okay. So we use a PCI device. Actually, this is a FPGA device, and then we program this device so that it can generate 1 millisecond timer interrupt. And this is very precise. Okay. Then we measured the latency. And actually, this is better than cyclic test. The reason is the cyclic test, I think yesterday somebody pointed out, but the results from cyclic test includes the time to program the timer in the guest. So for example, if it uses a deadline timer, then that causes a VM exit. Okay, so that basically includes the time to program the timer, and also the cyclic test itself runs in user level. Okay. So the scheduling in the kernel are also included there. Okay. So I'm now switching gear to the inter-VM communication. Okay. Before that, I want to talk about the communication model. Roughly, we have 2 of them. So one, depending on the API, the program model you use. So API, there is specific API. What I have in mind is, for example, like a DPDK. Okay, and in this case, this switch directly talks to the NIC, for example. Okay, then this guy provides some shared memory, so that the processes can talk with to the switch or the receiver send the packets. Okay. So packets go like this, when I just replay, okay. When the packets want to send the VM1 to VM2, you go to this switch and like this, okay. That's when you use the specific API or something like a DPDK. So there are other way which basically provides a network semantics. If we, for example, use the OS, right, that provides the network semantics, then you use a networking API. So in this case, I'm not recommending this one. This is the slowest path. So it's very slow. The reason is, the packets go through the hypervisor and the vSwitch in the kernel, and then causing lots of or transition and sometimes copying, right? So that's slow. And in NFV, we don't do this, right? So then we have a vhost-user. Essentially, vhost-user allow this vSwitch to directly access that the vert queues of the guest. Okay, so that's the way. For example, if VM1 send to the other VM, then I'll do the plugin. Okay, sorry, oops. This is a slow case, okay, and then this is a vhost user case. Okay, go like this. So we bypass the kernel, and then of course the vSwitch knows about the switching rules thing, right? And this is a typical way. For example, we have OBS, DPDK, then with vhost user or snub switch. Okay. Now, how can we make it even faster? Okay. So if we use a specific API, what we can do is basically don't talk to the switch. Okay. So something like this. This way, the VM1 can directly send a package to the VM2 without talking to the or bothering the switch. Okay. Now, if we have a networking API, then what needs to happen? So what we need is something like in-VM switch. Okay. Basically, we cannot send the packets ignoring what switch says, right? So we have to have some small cache of the VM switch that has a cache of the V switch, basically. Okay, I'll talk about more detail later. Okay. So in this case, the packets go like this. Okay. So now I'm talking about the implementation and kind of a proposal based on vhost user. Because just to use a vhost user shem mem. Okay. So what we want is, first of all, we want to add fast paths in the VM to optimize the inter-VM communication. Okay, that's what we need. So you see the in-VM switch here. Then also, whenever you want to send a packet, we want to send the packet from here to this. And if we don't have this fast paths, what the vSwitch does is, with the vhost user, he just access from here to here, this vert queue here, right? Then, like I said, this in-VM switch cannot ignore what the switch says. So it must have consistent, for example, flow table. Okay, that must be consistent and should be cached. And also, if this is optional, probably, but when I talked about this kind of feature, some people said this is great because VM1 in this case can directly access other VM, right? This is kind of dangerous. Even you trust, this is dangerous, right? So somehow we need to add some protection to the access. Okay. So the idea we have is basically we open the window when it's needed, and we want to close that the window if that's done. Okay, and of course without overhead. So you could do this by doing like a hypercall, right? Before the sending, you hypercall, then copy, and if you're done, then hypercall back, something like that. But that would be heavy, and so we're trying to avoid that kind of situation. Okay. So when we design, this is design objectives. So what we want is, first of all, extend the existing vhost-user as a transport mechanism, and that mechanism will be based on the shared memory or bird queues. So once we have this one, basically we can deliver packets to other VMs, okay, and they can access the bird queue directly. And that would require mapping of the guest memory, and also, like I said, the protection of access. Then on top of that, then you can build high-performance network applications. For example, the in-VM switch is one example. Okay, or you can provide service chaining. Okay, or maybe your application, NFV application. So now I will talk about a bit more details, okay, how it works. So this is what we have today. I just, I didn't, I have a more detail, but this is the same, topologically, it's same thing. I just rotate the picture just a 9 degree. Right. So this is basically OBS, DPDK. You have vhost-user support, and this is a QEMU, okay? This is how vhost-user works, okay? I didn't add anything, okay? This shows that how it works today, okay? So what vhost-user is basically gather the information of memory information, okay, from our QEMUs. QEMU has a file descriptor for the memory region. Maybe it's hard to see, but this is basically says base address of a guest memory, and then the length. So it's basically memory map table, okay? So vhost user server, okay, gathers such information from QEMUs, okay? So in a way, this server has, of course, he has today ability to access that, VMs, because he needs to access the bird queues, okay? Also, this is probably our one of the proposal, but he could also allocate his own memory, then make it shareable. Make it, the export that kind of shared memory to the guest QEMU, QEMU or VMs. Okay, for example, he can allocate large pages, then make it shared among the guests. Okay. Now, this is a bit busy, but the only difference is this kind of orange thing. Okay. In this picture, you see this orange one. Orange one is BM2. Okay. So this is a memory information on BM2. Okay. And this picture shows that BM1 has the access to BM2 memory, basically, okay? And also the other BM has a kind of same thing, okay? So how does this work? Okay. Well, so initially, vhost-user has this kind of information, right? Then he can actually, he was a server, but he can be a client and then send back or send this information to other VM, okay, so that QEMU can be the server, okay. So this allows that the vhost-user client to access the bird queue of other guests, or that allows to have a shared memory among the clients. Okay, so I have a more example. This is the simplest example, probably. So in this picture, VM1 already talked to this vSwitch or vhost user. Okay, again, this is, for example, OBS, DPDK, or snap switch. Okay, so he has the memory info of VM1. Okay. Now, VM2 is booted, and then he will also use this one. So first thing is he's going to send the memory map, memory table to vSwitch. Okay. Then he'll get the information, okay, of a memory map. Then he will send to the information to the QEMU. Then he can now QEMU extend that mapping, and he can map this one. Now the VM1 can access VM2. And we have the device, that PCI device here, and that's basically showing the base address of that shared memory. Okay, you can ignore that this the control structure for now. And once, sorry, I just keep one thing. Once that the QEMU add the memory, to the VM2 memory to the VM1, then QEMU inject the interrupt to the VM, then the VM will get the notification. Now, I have more memory. So it's kind of memory hop plug, or in this case, device hop plug. So this is now I'll talk about how we can add the protected access. So this picture shows the default EPT. EPT is extended page table that maps that the gets the physical address to machine physical. Okay. And in a default view, it's just a mapping that the existing gets the page table, and then gets the memory. Then we have a vmfunc instruction that's available in guest, and vmfunc 0 means switch the EPT. And then if the new EPT has additional mapping, then in this case, you can access the additional area. Okay. Then you can get the more memory. The VM2 can access more memory with vmfunc. Okay. Okay. I have a bit more detail. So in the fast pass, in a default view, the memory to the other VM, memory of other VM is not accessible in a default view. And if you do vmfunc, then basically that will be visible or accessible. That's basically how we add the protection. So we are proposing a new KVM IO control for the QEMU to extend that guest memory. One option is without protection. In this case, you trust the VMs, okay? So the window is always open. The other option is no, we need a protection and extend only in alternate EPT. Okay, that's the kind of proposal we have. Oh, this is a very detailed, gory detail, so I'll skip this one. But we use this EPT permission to control that, for example, in a default EPT, you don't have any access here because the EPT permission is none. Okay, there's a trampoline code page, and this is protected code that has access to additional page. Okay. So I have performance data from POC, and so far this is what we get. So the orange line is just a memory copy. Okay, we don't do anything. So this is kind of theoretical performance. You cannot beat this one. This is just a memory copy. Do nothing. The other one is just a VM func. Okay, no trampoline page. Okay. Then the third one is it's closer to actual case where we use a trampoline code. Okay. And then roughly we're getting this kind of performance, using the small packet like a 64 byte. And this is something like, even this one is like a 40 gigabit kind of thing. 10 gigabit, you get 14.7 megapacket per second. That's a 10 gigabit with 64 byte. Okay. So this is a summary. So I talked about, quickly go through this, minimal latency project, and then inter-VM communication. So propose that, vhost-user-based shared memory, and then show the performance data, preliminary performance data. And we are going to talk about the fast live migration next at different room. Okay. Any questions?
Yeah, just a quick question. So like for IPC, in different VMs, do you guys still have to inject the IPI? Inject it into it?
IPC? Oh, okay, so in this case, the receiver is in this POC. Receiver is basically polling. Yeah. In this case. Eventually, we're going to use, for example, posted interrupt to kick push that send a notification. But right now we're using polling on the receiver side. But the sender side is just a push, right? So that's what the POC is doing.
Yeah, I'm sorry. What did you say? So what you guys gonna use?
So we have the hardware has a so-called posted interrupt. Basically, that can inject interrupt to the guest without causing VM exit. Yeah. Anyway, if you guys are interested in join that OPNF project, sorry, go ahead.
So you have throughput numbers. Do you have any latency numbers for this kind of communication?
Do we have a red?
We have some numbers, especially about the interrupt that would not be. Here it's like pretty close to memory copy because it's polling on receipts.
No. Okay, I think I'm done. Okay.